Welcome to NEBULAB, a powerful browser-based acoustic modeling and simulation suite designed for fast exploration and serious analysis, all in one place. If you're a new user, you'll first need to create an account. Click Create Account, enter your email, choose a password, and submit your registration. Once your access has been approved, you'll simply return here and log in using the same credentials you created during registration. And just like that, you're in. Before we run our first simulation, let's take a quick tour of the interface. At the top is the header, where you'll find high-level actions and project-level controls. On the left is the control panel, which is where you'll spend most of your time setting up sources, receivers, simulation settings, and auralization options. On the right is the properties panel, which shows detailed settings for whatever object or tool you currently have selected. Along the bottom is the acoustics data panel, sometimes called the results panel. This is where NEBULAB organizes analysis views, measurements, and computed results. And in the center is the 3D viewport, where you'll build, inspect, and experience your space. Nearly every panel can be resized. Just grab the dividers and drag to make space where you need it. You can also temporarily maximize panels. Any panel except the 3D viewport can be toggled full screen, and then returned to its docked layout. Now let's talk about navigating the 3D viewport. In orbit mode, you rotate around a point of interest, which is perfect for inspecting geometry and layout. In walk mode, you move through the space from a listener's perspective, which is how you'll experience walkthroughs and verify placement for sources and receivers. Alright, let's set up your first walkthrough simulation. One note before we begin. The settings in this video are intentionally preview quality. The goal is to learn the workflow and get a fast, useful auralization. When you're ready for publication-level accuracy, NEBULAB gives you deeper controls and higher precision options, but those come with higher compute cost. Step 1 is choosing a simulation preset. For this demonstration, we'll load the concert hall preset. NEBULAB includes many other starting points, such as home theaters, office layouts, and studio control rooms. And if you already have a model, you can import geometry from tools like SketchUp, Revit, or Rhino using common formats such as OBJ, GLTF, GLB, STL, FBX, and DXF. Next, let's define the sound source. Choose a source from the list. For this demo, we'll use a preset acoustic source. Because we're using a voice sample, it's worth spending a moment on radiation and directivity. Human voice is not truly omnidirectional. Most of the energy projects forward, and that directionality becomes more noticeable as frequency increases. So we'll choose a forward-weighted radiation setting and orient it in the direction the speaker would naturally face. Now let's set Q, the directivity factor. Q is a simple way to describe how focused the source is. Higher Q means more energy projects forward, which can noticeably affect clarity, early reflections, and the sense of distance during a walkthrough. For voice, we'll keep Q in a realistic range. Directional enough to feel like speech, but not so narrow that it starts behaving unrealistically. Now set the acoustical loading to full space. That's typically appropriate when the source is not close enough to a major boundary to behave like it's effectively coupled to a wall or the floor. Next, we'll set up a receiver. For this example, we'll use ambisonics receiver mode, and we'll set it to the highest receiver settings available, so we capture the most spatial detail NEBULAB can represent during the walkthrough. Now it's time to move to the Simulation tab. Here you'll find options ranging from fast previews to high-precision, publication-ready runs. For a quick walkthrough, we'll choose the Balanced preset. Under the hood, NEBULAB uses a hybrid approach that combines ray tracing with a wave-based solver using FDTD, or finite difference time domain, which helps capture low-frequency behavior more realistically. For this simulation, let's increase the ray count from 25,000 to 50,000. In high-precision workflows, you can push much higher ray counts, but for a quick demonstration, 50,000 is a great balance. Next, set the reflection order to 4 to capture more early reflection detail. And since this is a concert hall, set the maximum time to 4 seconds. From here, we'll enable a few advanced options. Turn on the radiosity solver, which can improve realism and stability in many scenes by better accounting for diffuse energy exchange. Next, enable the FDTD wave simulation to improve accuracy in the modal region, especially below the Schroeder frequency, where discrete room resonances dominate. For this particular example, we won't enable ray transmission, since that feature is most useful when modeling sound passing between adjoining spaces. But we will enable impedance boundaries using the Mickey impedance model, which allows more physically grounded boundary interaction than simplified absorption-only approaches, including angle-dependent behavior. And while it's not enabled in this build yet, edge diffraction modeling is on the roadmap for a future NEBULAB update. Next, let's choose our spatial IR mode, which controls how directional impulse response data is encoded. Since we're using ambisonics, we'll set spatial IR to third-order ambisonics to preserve the highest spatial detail for this demonstration. Now let's pick an audio source for the auralization. NEBULAB supports standard test signals like pink noise, sine sweeps, and hand claps. But for evaluating the character of a space, it's often more useful to use anechoic recordings of real sources. Let's choose this example of a singing voice from the built-in library. You can also upload your own audio files for testing. Uploaded audio remains private to your account, just like your imported models and personal assets. We're in the home stretch. Before we can enter live walkthrough, we need to choose probe spacing and bake the probes. In NEBULAB, probes are sampling locations throughout the space where impulse responses are computed. During walkthroughs and flythroughs, NEBULAB interpolates between nearby probes to create a smooth, continuous acoustic experience as you move. Higher probe density generally improves spatial accuracy, but takes longer to compute. Lower density bakes faster, but with less spatial detail. For this example, we'll choose a conservative 2-meter probe spacing. Now the final step, bake the probes. Bake time depends on your model, settings, and hardware, and it's always a balance between speed and fidelity. While you're waiting, keep an eye on the acoustical tips that appear along the bottom of the screen. And now, we'll fast forward so you don't have to watch the progress bar slowly achieve enlightenment. All systems are a go. Now it's time for the star of the show. Let's enter live walkthrough and experience the acoustics of our environment as if we're really there. As you move through the space, listen for how the room response changes with position, distance, and angle relative to the source. You'll hear differences in early reflections, clarity, and sense of envelopment as you explore. You can also toggle the probe visualizers to see the sampling structure that makes the walkthrough possible. That's it for this introduction. This video only scratches the surface of what NEBULAB can do, from deeper analysis views in the acoustics data panel to advanced simulation controls for higher precision results. When you're ready to go further, open the Help menu to explore documentation and feature guides, and take a moment to click through the tabs in the results panel to see the different ways NEBULAB presents acoustical data. Thanks for joining us for this first look at NEBULAB. More videos are coming soon, and we can't wait to explore with you. See you next time.